grade forgiveness on it and get the
Yeah, but I
material.
mean, you have to take it again either way, so.
Going live.
Going live? Alrighty. So, assuming everyone can hear me, my name is Zach Fitz. I will be leading this 2-hour review session for Dr. Mackey's statics final exam. For those coming in, if you could please just sit on this side if possible, because my back has to be over there for where the dot cam is. So, how this session will work, I have 4 problems with roughly 30 minutes per problem. I'm still going to ask you guys to guide me through them, but if things are slowing down, I will push the pace a little bit to get through all of these, and hopefully with a little bit of extra time to do an additional problem or answer any more questions afterwards. So, assuming everyone else is ready, we will just jump right into the first problem. It's a machines problem from chapter 6, problem 82. The vice grip, very similar to one we did on a quiz or a test or something. Forget what it was. But you have this nice fancy vice grip that's a pain to draw. But as you can see, we have a load applied, and it's asking us to find the force on shank A. So, as Dr. Mackey has said 100 times, we always start our problems with our assumptions. What are we assuming to make this problem work mechanically? So there's one big detail in this problem that we have to assume or we just can't continue because we're not given enough information to do it otherwise.
Does it have to do with the at point A?
No, it has to do with every single member. The shank and every member there.
Apart, right?
Well, yes, but the detail we have to assume is that all of these members are massless. None of these members, once we separate them, have their own mass. Otherwise, there's complexities in the calculations we can't solve. So, if everyone has, well, I'll give you guys another minute to copy that down, or just let me know when you are ready to start the problem. So as you're drawing, is there anything else that we should take note of for where to start this problem? Somebody already mentioned exploding the machine and separating the members.
So we're going to probably need to recognize that CD, there's a 2-force member, right? That's going to help us quite a bit because we can start on either end, but it's probably better to start on the bottom and then work our way down.
Yes. So I'm going to repeat most of what you said so that they can be heard through the microphone a little bit better for the live stream. But yes, once we separate these members, we are going to realize very quickly that member CD is a 2-force member. So that one will probably be the easiest to solve for. Well, actually, let's look a little bit closer at it. Will CD be a 2-force member?
Oh, is it not going to be because of the 5-force down on it?
Possibly, because there is that force there. So it's still a good starting place because it looks like it will be. So if that's an agreeable place to start, we'll start there with the analysis. Are you ready to jump in? I have the drawing on my page also. It's a little bit more crude, but it gets the gist of the information. And I'll have this one here if there's any questions of clarity. So jumping into that problem, we're going to start with we're assuming there are massless members. So now we're going to explode the machine. So, especially in this step, the the artistry of your problem really goes down the drain. It doesn't matter how good it looks as long as it's roughly close. So please don't spend a lot of time on your final exam drawing really neat, fancy free body diagrams. As long as the information is conveyed and it's generally close, you'll be fine. So. All right. So now we have 4 separate members. And we'll label the points that we know, C, D, C, E on that one, E and B, and then B and D. All right, so with the forces that were, with the external forces that were applied at D, we have a force applied there, and a force applied at some arbitrary, not arbitrary point, 3 inches away from point C. Will this external force here applied to this member also be applied to member CD? Not for that reason, but it will not be applied because the force is applied to this member here that contains BD. Yes, although the force is going through point D, that tells us there won't be a moment about D from that force, but the force is not directly acting on member CD. So that force will go into this member and will be combined with the reactions at D because of that. Maybe not directly, but it will be accounted for by the reactions. So that being said, we know CD is still a 2-force member. So if we'd like to start with CD, draw it again, and we know that whatever its forces are, they're going to be along the axis of the member. So FD, FC. But do we have any information that can help us solve for those forces? Well, how would we solve for those forces?
Well, because it's a 2-force member, wouldn't we set them equal to each other?
We would, but will that accomplish anything at this moment?
Could we go down to like EC down there, and we know, and we could sum a moment about, maybe about E, because we know the force there, we just wouldn't know C.
Yes. So, long story short, we cannot do anything with this member yet other than make statements. We can say that FC is equal to FD, or resolve it into components and say that, excuse me, that FC in the x direction is equal to FD in the x direction, but we cannot get any other information from it because there's no other information given there. So if we start at member EC, we have a 5-pound force applied 3 inches from C. And then we also know that C will be 1 inch from E. And I'm sure you guys are aware by now, nomenclatures for feet and inches. A apostrophe is shorthand for feet, or opening or closing quotes is shorthand for inches. So that can save time. That's widely understood. You won't lose any sort of points for that that I've ever heard of. So if you're crunched for time, don't worry so much about writing inches or feet. Just do little tick marks, and it's still understood. So with C and E, what kind of reactions do we have at those points on this member?
Since they're pins, we've got the U of X, U of Y, and C of X, C of Y.
So it's assuming positive, because that just makes analysis simpler. We now have 4 unknowns. So how do we want to start? Or can we start?
Can be some forces at C, or at E, actually,
Some forces?
or some moments.
Do some of the moments at E? All right. And what will that accomplish?
Well, we would get CY because we've already got a force over there, which we know the distance from.
Yep.
And CX runs collinearly.
Yeah, you can't really see it in my diagram, but looking back at the original, C and E are in the same horizontal line, so CX will act through point E. So if you take a moment about E, 3 of your 4 unknowns will disappear. We can find CY. So if we do a sum of the moments about E is equal to 0, we go 0 is equal to our 5-pound force acts through a distance of 4 inches. Yes.
Are there any papers there?
No. You can't see it too well. I'll try to zoom this out and get the problem on there also. It's problem 82. Where's my focus? There we go. Oh, you can sort of still see the diagram. It's this problem here. So going back to a moment at E, we have, do we want to work this problem in inches or should we translate it to feet? It's a bit more common of a measurement. Keep it in inches? All right. And again, there's no wrong answer to that. It's as long as you're consistent and you mark your units at the end, you'll be all right. So keeping it at inches, we have a 5-pound force times 4 inches. And that moment, the moment from the 5-pound force around point E, will that be a positive or a negative moment? Positive moment because it's rotating counterclockwise. Then we also have a CY times 1 inch. That force, the direction we assumed, will it cause a positive or a negative moment? Positive moment. So that leaves us the equation 0 is equal to 5 times 4 plus CY. So we know CY has to equal negative 20 pounds. So what does that tell us about the directions we assumed?
They're opposite.
CY is going to be the opposite direction. So cross that out. We now know CY is down there, and it's 20 pounds. So how do we want to go about the rest of this member now?
Can we go back up and finish evaluating the 2 force members?
We only have part of the force at C, though. So again, we can get some information, but would we be able to finish it with only CY?
So can we say, aren't they equal to each other? So can we find CX by summing a moment there at C, and then we know CY is equal to DY?
We would find DX that way, yes. So we could jump back there now. But do we want to get any more information from this other member first, or do we just jump back to the other one?
Oh, we could get,
I mean, either one is fine. It's how do you guys want to solve the problem?
it looks like E is going to be necessary for, or that body with E on it is going to be necessary for solving the rest of the problem, so we can sum a moment at C.
All right. So if we also do sum of the moment at C is equal to 0, 0 is equal to, slide that back down so you can see. Now you have the 5 pounds times a distance of 3 inches. And is that a positive or negative moment? And then you have EY times a distance of 1 inch. Does that cause a positive or negative moment? Negative. So that also tells us that EY is equal to 15 pounds. Positive in the direction we assume, so we know it's correct there. Yes.
So what is negative EY again?
Why is it negative EY? Because when we took the moment about C,
Okay.
the EY force and its distance will cause a clockwise rotation. So it's probably also better to write up here near your assumptions at the top, your positive sign convention. That way, even if you chose completely opposite of that, as long as you identify it and they can follow your work, if your answers are different than what the answers are supposed to be, quote, unquote, as long as your sign convention is correct, you'll still be correct. So now with CY and EY, is there anything else we can get from this other member? I mean, we can do some forces in the X, but that again just leaves us with an identity. EX is equal to CX. So that doesn't accomplish anything. So now let's jump back to that two-force member.
Do we need to go back to the two force member, or can we just keep moving along the bottom?
We could move along the bottom also.
Because it looks like if we get the information for D, that's to help us solve the top, but we're already working on the bottom. So it makes sense that we would just continue to work along the bottom to get the answer we need.
But if we went to that two-force member and did a moment about D, we could get CX, which would then lead us to EX. And that will help us moving along the bottom. Because we'll run into a similar problem with the next piece along the bottom, where we'll need EX and a BX to solve for that. So if we jump back to this member, I'm going to switch pages real fast. We'll redraw that diagram. FD, FC. We'll split those into components. And you know what, we don't know for sure, so let's assume positive again. For anything we don't know for certain, we assume positive. We know this one is 20. And now, do we know the distance between C and D? Yes. It was 3 inches horizontally, and I believe, since D is in line with B, 1.75 vertically. So if we do the sum of the moments about D equal to 0, 0 is then equal to 20 pounds times a distance of 3 inches. And is that a positive or negative moment? Positive. Starting here, pushing down, we'll rotate counterclockwise.
So even when we know it's negative, we still treat it as, we just assume that it's positive until we get like the correct moment direction.
Yeah, that's just something I picked up when I was taking this class. When you're dealing with moments, the direction of the force does not matter, other than will it cause a clockwise or counterclockwise rotation. So I learned that you can ignore the sign of the force as long as you correctly account for the direction of rotation. But that being said, we also know that since we wrote y or cy pointing down in this diagram, the 20 here is positive because of the direction we assumed. And that's how that works out. If we still wrote cy as pointing up, then we write it as negative 20, but since it's pointing up and it's a negative 20, that makes the moment positive also. But if we jump back in here, we have the cy times 3, and now we have a cx times 1.75. And we'll CX, in the direction we assumed, is CX a positive or a negative moment? Positive. So we solve for CX. CX is going to be 60 divided by 1.75. And I hope somebody has a calculator because I don't. 34.3 pounds. Yes. Welcome, welcome. All right, so now we have CX and CY. And on this first page, I will make a table over here. That's everything. Every member we've looked at, those are our 6 unknowns that we had. We now have CX is negative 34.3, CY is negative 20, EY is a positive 15. If we're working along the bottom, we know we're not going to need DY, at least not yet. We shouldn't need it at all. So now that we have CX, what should we do? Yep. Now, from EC, with a problem like this where you're constantly switching members, anytime you're going to write an equation, if it's not right next to a free body diagram, always specify what member it's from so that they can look back at your diagrams. So from the EC member, we know that EX is equal to CX. With the directions we assumed, negative EX is equal to CX, because we assume both to be positive. So if CX is negative 34.3, that equals a negative EX. EX equals 34.3 pounds. So if we look back at our free body diagram real fast, we also found CX to be negative. So now analytically, although the diagram is hard to see, does that make a bit more sense? You have a positive force up here on this edge, a positive EX, a positive EY, and CY and CX are both negative to counteract all of those other forces. So analytically now, that makes sense. Where should we go on from there?
We could move on to the EB body.
Okay. So
which direction is EX going?
EX is positive.
But which way is that going? Oh, to the right.
On this diagram,
Yes.
it's going to the right.
I like to do more my forces in which direction they're going.
Yep. So now that we've switched members, does that change the direction of those reaction forces?
Not really, we still draw the positive sign.
Still draw a positive sign convention. So we can get these out of the way. So we have an EX, an EY, a BX, and a BY. So EX was found, I'm adding to the table over here, was 34.3. And are there any other forces acting on this member? Oh, yeah, sorry. Are we sure?
I mean, technically, we're going to have like the AY, right?
There is a reaction force from the shank resisting the clamping motion of the vise. So there is going to be a force right there from A. All right. So what do we know or can we know about A? Is there anything? That's what we're trying to solve for.
So it's an unknown for right now.
So for right now, it's an unknown. So with that in mind, how are we going to get to that unknown? Because right now we'll have two unknowns from B, and we have to resolve A into components, so there's going to be two unknowns. Do we have enough equations to solve four unknowns on this member?
Is A collinear with B?
No, it is not. I know it kind of looks like that in my diagram, but going back to the original, no.
And so if we were to sum moments about B, we'd still have to take A into account, we don't know what that is.
Yep, we still have to take in two components of A. So with four unknowns on this body, do we have enough equations to solve for it? No. So we have to then go to a different body instead. So we'll go to BD. Well, before we go to BD, why don't we hop back to CD just for a half second and identify that, yes, CD, or dx and dy are equal and opposite to cx and cy. So going back to our table here then, dx is going to be 34.3, dy is 20. Now we'll hop over to BD, where we have something like that. Right. So what can we solve for in this situation?
We can sum forces and the x to find bx, which is going to be
Well, there's still an x component of A.
all.
Take moment around A or B. Is A collinear with B on the top? Does not appear so. No. So that'll still leave us with two unknowns. So with the theta given, this way is in, A is rotated, or the plane of contact with A is at a 20-degree angle. So we know that that angle is 20. Zoom back out so we can see. So then that tells us that that's 90. Dum. That would be, yes, let me turn that off. So we will try to get through the rest of this problem quickly, because that should be moving on to the next one. AX will be at that direction. If that's 20, then that should be 20 also, correct? Is that correct? Double check my geometry, please. No, this one would be 70. All right. And then a y component would be if we can keep the 20 to get a y to a y component. Let's say hypotenuse there, so that cosine 20 is a. So yeah, a cosine inverse 20 is the y component, I believe. So then where should we go in solving this problem then? Moment about B.
We solved the two unknowns with A, right? So we got the AX and B1.
What are the thoughts about maybe using a different set of axes for A, so we don't have to resolve components? Because we know the geometry there, can we leave A as just A in, say, a y prime direction, and use that geometry to get bx, by, and dx, dy into that coordinate system? Because then geometrically we would have numbers for dx and dy, and then we would have bx cosine or sine of some angle and by sine or cosine some angle, but then we would only have an A. So then we have three unknowns, and between moments, some forces y, some forces x, we have enough equations. So when we get to this last member, let's change the coordinate system. So we'll start that on another page. So now I'll redraw that diagram so we still have it to work with. All right, so to get to a new coordinate system, we'll assume that A is in the y prime direction, positive. So we've taken our standard coordinate system, and now we've rotated it 20 degrees. That one's an X, sorry. So that's what we've done there. So now how do we translate our dx and dy and this 5 pound into that coordinate system?
We just tack on, it's like, it'd be cosine 20 right now. That would be sine 20.
Yes. So we then know dx was in that direction. That's 70, so that's 20. Dx times a cosine of 20 gets x prime. Correct? We'll need to draw this a little bit bigger so it's easier to read. This one was given as 20, so we know this is 70, and that then in turn is also 20. We have dx going this direction, so dx cosine of 20 would leave it in the positive x prime direction. So dx prime is equal to dx cosine 20. We'll move over here so I'm not intruding on that. dy prime then is going in this direction. So if this is 20, this is 70, that's 20. dy cosine 20 gives a dy prime that's positive. All right. We then have a negative 5 pounds times a cosine 20 is a dy prime that's negative, or not a dy prime, but the 5 pounds cosine 20 is the y prime direction, and then sine of 20 is the x direction. And because of that geometry, we know that if the 5 pounds is acting down, it's going to be a negative and a negative in this new system. And now we can just label bx prime as the new unknown, by prime is the new unknown. So we don't have to do any more conversions there. So now we have that's our new free body diagram then. Dx prime, dy prime, bx prime, by prime, ay prime. And there was also a 5y prime, 5x prime. Now we can solve this one with a moment about B. Since we're asked to find the force at A, we can skip solving for B altogether by just doing the moment about B. So some of the moments about B is 0 is equal to dx prime and the 5x prime are collinear with B. So those don't come into play. So we have dy cosine 20 times a lever arm of B to D is 4 inches. And that will cause a counterclockwise rotation, so it's positive. Then we have 5 cosine 20, and I think at the same 4 inches. And that causes a clockwise rotation, it's negative. Then we have A acting at 1.5 inches. And that will give a clockwise rotation, so it is also negative. So then A is equal to dy cosine 20 times 4 minus 20 cosine 20 all over 1.5. And yeah, we know dy from before, but for the sake of time, you guys can throw that in a calculator and get that whenever. But do all the steps there make sense? So if that question is all right with everyone, we will move on to the next one. This one unfortunately isn't in the book, but it's a lot simpler to draw. It's a shear moment diagram. We have a distributed load. We have a pin here, a roller there, and this is a free end. We have a distributed load, 2-point loads, and a external moment.
Point loads have force like associated.
Yes, but I didn't come up with a number, so give me any number.
How about 10?
Another 10. And what about someone else? Give me the number for this other point load. Just pick a number, any number. 15. All right. So how do we start any sort of internal force problem?
Well, we do the reaction forces.
Find the reaction forces. How do we do that?
Center moment regular.
Or more generally, external or global equilibrium. So we know that this is going to have a y component and an x component. This is only going to have a y component reaction. If I label those A and B real fast, we need a x, a y, and by. So how do we go about finding any of those?
Well, we need to know the resultant force, right? The triangle up there.
All right.
So can't we do that because it's two triangles next to each other? Can't
Yeah.
we treat it as almost like how we would find a rectangle, right?
Yep. So what he's saying is that these two triangles here, if you want to think about it that way, this half of the triangle fills in this other half of the rectangle. So we really have a 10 by 5 rectangle rather than a 10 by 10 triangle. So that would give us a 50 Newton force total there.
And that happens right in the middle, right?
And that would happen right at the middle, and we know that easily because of symmetry. Rather than trying to do centroids, all right. So we've resolved that distributed load into a resultant force. Where do we start with our global equilibrium? Moment about A. And what is our moment about A? Like, what are our components of that? What's the distance for the 50? 50 times 5. And is that 50 times 5 positive or negative? Moment about A, clockwise, yes, negative. Then we have by times 10, positive or negative moment? Positive moment. Then we have this 10 Newton force times 15, negative. We have this 15 Newton force times 20, and that is a positive moment. And then let's call that external moment is 30 Newton meters, we'll call it. Because I was sloppy in making the problems, apparently. And is how that external moment is drawn, is that a positive or negative?
It's going to cause a negative moment.
That's a negative moment. It's negative 30. So someone throw that in a calculator real fast and give me By. $250 plus 150 is 400. Negative 400 plus 300, negative 100 minus negative 130 to negative 13, negative 12. Got negative 13 in my head, but $13?
Did you account for like the negative 50 times 5? I forgot.
Yep. Negative 50 times 5. And that's 400. Then the 15 times 20. There should be a 100 plus 30. Divide by 10.
So it's
13. So By is equal to 13 newtons. Then we would also, our next step, we'll do some of the forces in X real fast just to see AX is going to equal 0. And some of the forces in the Y equals, we had a negative 50, have a negative 10, a positive 15, then a positive 13, and a positive AY. So negative 45 plus 13, negative 32 for AY. Or no, yeah, positive 32. Moving those over to the other side. AY is equal to 32. So now that we have all reaction forces, all that's left is our shear and moment diagrams. I'm going to slide that over so it's a bit more right underneath this. Drawing straight lines is always nice. All right, so how does our shear diagram start? Discontinuity from AY. So it's going to go up by 32. All right, now what?
You have your triangle roads right there, and you take them like piece by piece. You have one that's, it's going to be parabola, that's going to be getting more negative as you go down. It's going to reach a point.
All right, so it's starting at a positive, or starting at 0 slope, and becoming more and more negative. So it's going to down like so, but how far?
Isn't it going to go down 50? But it's like that's the
Not 50.
negative 50.
What's the area of this first part of the triangle? Because we have to do 2 halves of the triangle this time, because there's differences there. So right now we're only looking at the first 5 meters of the triangle. So within that first 5 meters, we're going to go down a total of half of 50, or 25.
How do we determine concavity again?
I look at it less as trying to decide, is it concave up, concave down, and more of it as, what is it doing? Right here, we're starting with 0 negative force, and the force is getting more and more negative. So the slope is also getting more and more negative. So starting at 0 wherever we were, and our slope gets more and more negative up to that point. Now we're starting with a negative slope here. It's still going down, but it's getting more and more, well, instead of more and more positive, it's less negative.
So we switch it to
So at this point, at the 5 meters, it's going to change concavity because the distributed load changed. So it's still going to go down by 25 more. Also, what's 32 minus 25? 7. So it's going to go down 25 more, but get more and more positive. So 7 minus 25, negative 18. All right, then BY was 13. It's a discontinuity. It's pointing up again. So we go up by some amount. Negative 18 plus 13 gives us 5. Not 55, sorry. All right, then we have nothing, no change, until we get to this 10 Newton force. We got 10 Newtons pointed down. We're going to drop down to negative 15. Then nothing for 2 more meters. Does this external moment do anything to my shear diagram? No. So we skip right over that point, go over to here to the end, go up by 15, we end at 0, and that is not by chance. So our shear diagram has worked out correctly. So now on to the moment diagram.
So we should calculate the areas under those curves or whatever they might be.
Well, you should end up at 0.
You got lucky with picking a number there.
Ooh.
0.
Well, no. Yeah, no matter what those numbers were, our reactions would have changed. Because we calculated the reactions right, then we ended up back at 0.
Okay, so regardless, it's going to be at 0.
Yeah, as long as we pick those numbers before we calculate reactions, it will always be 0, unless we screwed up somewhere. So if it's ever not 0, that's your big clue. Hey, what did I do wrong?
So if we're calculating the area of that first one, there's a formula for it, right? There's like the weird area formula.
Yes, there is. And you have that formula in the book? I want to say it's on one of the cover pages.
For the weird parabolic shape, up to 0.5. That's what we actually got a rectangle.
Yeah. We have a rectangle underneath a parabola. So that area, we know the area of a rectangle. That's a 7 high by 5, so that's 35. And then that parabola is 1/3, or say 2/3 base height.
Add them together, I got 118.
That was, where's the 25?
25 would be the 32 to the 7, the height.
Oh, yeah, okay. So 25 times 5 times 2/3, and you got, what was it?
I got 83.3 for 2/3.
So 83 1/3. So would add up to 118 1/3. Does everyone agree with that, to that point? We have total of 118 1/3.
This is our moment diagram.
I'm sorry?
Why are you seeing the shear?
Well, we're calculating the area under the shear so we know how much the moment changes. So the area up to this first 5 meters, our moment is going to change by 118 1/3. Then there's still this small distance here before it crosses 0. And then so we need to find, it's hard to see there, but if I can't really see that. Explode that area, it actually looks more like so we still need this area here before our moment changes direction. So how would we calculate that area?
Okay, so the missing component will be the distance because you have the height factor. You just need the distance before it. When it equals, we have to find when it equals 0, and then we subtract 5 from the original rate.
So there might be an easier way to do this.
An equation.
An equation. If we look back at our distributed load, what equation can we write for the first half of the distributed load? W is equal to 2x. It starts at 0 and goes to 10 over 5 meters. Rise over run 2x and starts at 0. So if W is equal to 2x on x equals 0 to x equal 5.
Can we use this equation for it?
We can, but then as we just found out, we still have this other area here.
So it's not covered by that, even though like there's the rectangle there and the parabola over there.
So then we wouldn't add the two together. It wouldn't be a parabola and a rectangle. It would, but
Because it would still cover that.
yes, but remember the concavity changed here, so the parabola is different.
Okay.
So this section isn't the same parabola as that section. So that's why that doesn't quite work out. So we kind of have to use an equation on this one and integrate.
Wouldn't the shape of it be, because it reached the point of inflection that it's doing this now instead of being concave like that, wouldn't the shape be, it would look more or less like that instead of like,
Yeah, my artistry is not fantastic, but yes, at that point was the change in concavity. So it's a bit more like that. But we still don't have a convenient way to find where that crosses 0. So if we use W is equal to 2x, we know shear is the integral of W, right? So start on a clean sheet. We know that so if we do that, you know Vx is the integral from 0 to 5 of 2x, which gave us exactly what we wanted. But let's do it in a definite or an indefinite integral and get an equation for the shear. So x squared plus c. Do we know any boundary conditions? Do we know the shear at any point? We know the shear at the very first point. So I'm going to clarify right here, this W is negative 2x because it's getting larger negative. So that's a negative 2 negative x squared plus c. And because the shear is equal to 32 when x equals 0, we know that c equals 32.
Well, we can need that negative in front of x squared, because x squared is going to be positive no matter what.
But with it being the negative in front, that tells us that the parabola is upside down versus right side up. So v of x we know is negative x squared plus 32. So now we need to know where that curve, well, that curve is never going to cross 0 on the interval 1 to 5. So now we need to do w of x from 5 to 10. So now we know it's starting at 10. So w of x is going to be 10. Well, starting at negative 10. And it's going to get less negative. So it's still going to be, or now it would be a 2x, correct? So wx is 2x minus 10. So then v of x is integral of wx dx and do we know anything about boundary conditions for this one? We know when x equals 5, c is c will be equal to, or not c, but v will be equal to 7. When we looking at this, it seems counterintuitive, but right here, since our forces are getting more negative, our slope was a -2, but now we're starting at a negative and going towards 0. So we know when x equals 5, v equals 7. So 7 is 25 minus 50 plus c. Seven plus 25 equals c. C is equal to 32. Again, ironically. And that isn't always going to happen. That's just coincidence. But all right. Now we know that v of x is x squared minus 10x plus 32 from 5 to 10. Now where does this cross the x-axis? We know this one has a 0. So we just set it equal to 0. So we know that x squared minus 10x equals negative 32. And solve for x. Looks like it's quadratic formula, which will be annoying, but is there a factorization? 10 and 32. 32 is 6 times, no.
Because with x squared, everything factoring out, right? Because we're trying to factor out 2.
Well, if the 32, if we leave the 32, leave it as a, does that have a factorization? What are the factors of 32? 8 and 4, but that won't work. So we got to do quadratic formula. Negative 10 plus or minus square root of 10 squared minus 4 times 32 times 1 all over 2. So 10 squared, 4 times 32 times 1. Actually doesn't look like this will have a actual root. What? B plus square root of b squared minus 4 times a times c. All over 2a. Getting non-real answers, right?
I got x1 equals -6.8, and then x2 equals 5.1789. I think I have polished up on my calculator.
Yeah, we get the calculator.
All right. So that means something is wrong here. Let's check what we did. It might be that 32. It is the 32? So.
Just to include that after 5 meters, it's at -18, so that works. Plug in 5 as x there, you get -18.
Well, not in this case, because we're saying that this function is valid. The x squared minus 10x plus c is valid from 5 to 10. So at 5, we're still at this point here.
You change the bounds, like instead of 5 to 10, it could be 1 to 5 if it's a distance of 5 meters.
Okay, I see what you're saying, yeah. It's valid from that point, but x is at the distance x is 5, the x in this is 0. So, yes. So that 32 is incorrect. It shouldn't work though, because no matter what you do, 100 squared minus 4 times 32, you're always going to have a negative inside your radical. So then we're plugging in a 0 instead of a 5 here, and it's going to equal 7. So 0 minus 10 times 0 is 0 plus c is equal to 7. C is equal to 7. We'll then change this to a 4 times 7 times 1. Now we'll have a real answer. Good catch. Thank you for that.
So that'd be
9.24. Are there any other roots, the plus or minus from the square root?
plus and then minus is 0.7.
0.76? Seems a little odd, but okay. So we have a 0 at 9.4. Did anyone confirm? Good? All right. So we know this point is actually at this point here. X equals 9.24. So then we need the integral of v. Go back to our moment diagram. To get from 0 to 5, we just need the integral of our first w from 0 to 5. That one, start on another sheet of paper, because these problems take way too much space. Integral of wx1 from 0 to 5 is... I'm sorry? Yeah. So we have a negative x squared from 0 to 5. We know that changes by 25. So from 0 to 5, our moment that starts at 0 will end up at a negative 25. But it should be positive 25. Because x squared, sorry. So our moment changes by 25, but does it increase or decrease by 25? I believe it was moments, he said, are backwards, like a positive moment.
Moments are backwards, yeah. Because if it's going clockwise, that's negative. When it's going counterclockwise, it's positive.
It's moving 0 faster, so it's not going up.
So is it going like this,
So
or is it going like that?
because it's a parabola up there, isn't that going to be cubic?
It's going to be a cubic either way, yes. But we're changing by 25, but are we changing by 25 above the axis or below? Above? Or
Well, I mean, it's going to have to be because whenever it crosses, whenever the shear moment crosses the 0 line, that's the point of maximum moment.
it's a point of maximum or minimum moment. It's a critical point, not necessarily a maximum. So I believe because of our forces, we're going to get a clockwise rotation about A. So our beam is going to bend this way. So that is a negative internal moment, I believe. Is that correct? If you get the frowny face, that's negative. So we're changing by 25 but it's going to be below the axis. Then we need to integrate this new function, the x squared minus 10x plus 7, from 0 to 5. Well, we need to do two separate integrals here. We have to go from the beginning of the function to the 0, and then from the 0 to the end of the function. So
should we draw like a basic shape of the moment diagram so we got one or two more questions? Because like obviously the integration.
yeah. Yeah. If everyone's okay with that, that sounds like a better idea. We'll just, okay. So it's going to be a cubic that goes down, then it's going to go down a little bit further until we get to that 9.24. Then it's going to shift and start going up. Since this is still parabolic, it's still going to be cubic. The discontinuity in the shear doesn't do anything, but now we're going to go up at a straight line. We're going to go up at a straight line again. Then we have a negative external moment, and then continue to go up at a straight line. I should have done that all on the camera, but it's cubic going down until 0.5, then it's cubic going down a little bit further to the 9.24. Then it begins going up at a cubic until we get to 10. Then it goes up at a straight line in this region. Goes up at a straight line again for these first 2 meters. Then there's the external moment that causes a negative discontinuity. And then it continues to go up at a straight line for that region. All right. So let's make sure we work on integration on our own time then, because obviously that took a while. So do we want to do a centroid problem first or a friction problem first? Centroid? All right, so centroid problem it is. And I didn't come up with the dimensions for this because it was in the book. Theorems of Paltus. There it is. Fundamental problems. Problem 12. I'll zoom in a bit more so you can see it. So we're finding X bar, Y bar, and Z bar of that composite body.
So we're at F912, right? The composite body?
Yes.
So this is the one that we were saying was similar to the one that we did for the collected homework, except we're not having like a 16 minus z gamma.
Exactly.
It's just solid throughout, so you don't have to do that whole
Yep.
calculation.
Same exact principle, except simplified for that reason. I wanted to do a problem just like that one, but didn't think we'd have time to get through that, and I'm glad I chose this because apparently I'm right. Time has been a bit of a problem, but we know the thickness everywhere is 0.5 meters. So it's a composite body. We'll separate it into 3 distinct bodies, find their centers, and then add them together with a weight. So the 2 triangles are not quite symmetric, so we have to do them as distinct bodies. So we have triangle 1 is 1 meter by 1.8 meters, like that, and it's the 0.5 meters thick. So how do we find our x bar of this shape?
It's going to be, you could do 0.5 plus whatever it would normally be for a triangle, so 1/3 base. So it'd be 0.5 plus 1/3 times the base.
So you're saying it's the 0.5 from the rectangular shape plus 1/3 from here. So 1/3 of 1 is 1/3. So we have 0.5 times 0.3, so 0.833 repeating is x bar. So is it safe to assume that you guys all know centroid of a triangle and centroid of a rectangle? So we can just use those rules rather than trying to actually calculate them with integrals?
Yeah.
Okay. So then y bar, remembering that y is up and down here, that's going to be 1/3 from this end, correct? So 1/3 up of 1.8 is 0.6. And z bar, or no, I had, yeah, I had those backwards. Z bar is 0.6. Y bar is 0.25. Now, triangle 2, it's almost the same, but not quite. 1.8, 1.5.
So can you just write down what the equation you're saying for the centroids?
With this particular problem, we're not using equations because we know the shapes, but generically it's x bar is integral of x dx over integral dA, right?
Yeah, okay.
And then y bar is integral of y dA over dA. But since we know it's a triangle, we know the centroid of a triangle.
Which is
1/3 times the base.
Yep, 1/3 times the base, or 1/3 from the big end, 2/3 from the little end. And for the y bar, it's rectangular in that direction, so it's just halfway, if that makes sense. So then x bar, y bar, z bar for this one. X bar is now the 0.25.
X bar, if you're up at the top, I think that for the second triangle, the x bar is going to be, yes, 0.25.
Yep. 0.25 from that one. Our y bar is now going to be 1/3 from here, but we have to add the 0.5 plus the 2. So 2.5 plus 1/3, 1.5 is 0.5, so y bar is equal to 3. Z bar is 1/3 of 1.8, 0.6 again. And then rectangle 1, it's 2.5. .8. So The Z bar is now going to be half of 1.8, so 0.9. The Y bar is half of 2.5, or 1.25. And the X bar is half of 0.5, or 0.25. Sorry. Keep forgetting that I have to move my paper. You can tell I don't use dot cams very often. I prefer whiteboards, but
So you said Z-bar, so why is it different than 0.6?
because now the centroid of a rectangle is in the center, not 1/3 from the base. Both the triangles, the Z-bar was 1/3 from the bottom, but now this rectangle is 1/2 from the bottom. So now that we have all 9 of our components, how do we find the centroid of the entire body?
You have some of the weight.
Some of the areas, and you weight them how?
It would be X bar, like the summation of X bar times the weights divided by the summation of the weight.
So summation X bar times W over summation W, like that. So what are our W's? How do we weight them in this situation? We would weight it by volume, not an actual weight, if that makes sense.
And so it's going to be a constant.
Yep. So
And then we're just calculating the volume of 2 different cubic triangles and then of the
Yep.
uh,
and the rectangle. Yep. So volume 1, we'll call it, I just turned that, instead of rectangle 1, just call it R3, so I can do V1, V2, V3. V1 is 1/2 times 1 times 1.8 is the area of the triangle. Then multiply it again by the 1/2 of the width to get the volume. Times 1/2, you said 0.45? That makes sense, because it's basically 1/4 of 0.8, or 0.18, sorry. V2 is 1/2 times 1/2 for the thickness again, times 1.8 times 1.5. So 0.67. And V3 is 2.5 times 1.8 times 0.5. So add all those together. You add those 3 together for me? 3.37. All right, so now we know the sum of our volumes is 3.37.
and then we have to do
So now we just need to do X bar times V for each component. When doing,
it'd be X bar times V, then Y bar times V.
yeah, X bar 1 times V1, X bar 2 times V2, X bar 3 times V3. So I always found it easier to do it in a table rather than keep track of it all this way. So now that we know X bar 1, how did I set up the tables?
You want Y1 below it and then have like
2, X
the
3,
triangles.
Y1, Y2, Y3, Z1, Z2, Z3. And these are all bar, but you guys get that. 0.9. Then V1, 0.45, 0.67, 2.25, 0.45, 0.67, 2.25. All right. So I've just labeled out each one of the X bar, Y bar, and Z bars, lined them up with their corresponding volumes, and then call it N bar V. Then this column, just multiply them straight across. So can someone fill these in for me as I go?
First one's 0.3.
All right, and then sum up the first three and give me that value, then the second three, then the third three.
The first three are 1.7. Uh,
4.93. $2.7. All right. So now X bar for the composite body is going to be 1.78 divided by 3.37. Y bar is going to be 4.93 divided by 3.37. Z bar is 2.7 divided by 3.37. I'm sorry, yep. And that's just going back to the formula of N for a generic term, N bar times V summation divided by summation of V. So those numbers aren't important. Are those steps clear so we can move on, or do we need to spend any more time on this problem? All right. So this one again is not from the book, so unfortunately you have to deal with this crappy drawing, but this one was simple. It's just a box on the floor. This is just a floor. Ignore that it also looks like a box. This has a center of gravity in the very center, 0.5 and 1.
This is a friction problem?
Yes. This is statics.
So the 0.5, that's distance over to,
That's the distance from the edge to the center of gravity.
so is the center of gravity lined up with P?
No, P is at a height of 0.6.
And, and so, wait, so what's the height for a G?
The height for G is 1. It's in the very center of the box. This again is, you can think of it as a homogeneous solid for the box instead of a box full of stuff.
Volume is pushing it.
Yes. P is unknown, we know the mass of the box is 4 kilonewtons, or kilograms, I should say.
So if P is pushing 0.6, would that be below G?
No, G is at 0.5. Oh, then yes. Yes, it would be pushing below G. But so let's call it 40 kilograms instead of 4 kilonewtons. That's a mass, not a weight. So got 40 kilograms in this box, 80 pounds roughly, or 90-ish. So pretty heavy box. And then actually, I want to change that. Instead of P being at 0.6, let's put it at 1.6, because I want it to be above G. What? It still could, but it'd be a lot harder to make it tip.
Make it tip and pushing below.
Yeah, if you push hard enough, if the friction is strong enough. If you're pushing below the center of gravity, 99% of the time it will slide before it tips. That's why you're supposed, if you're pushing, you're supposed to push from down low. But the question for this problem is, what will the force need to be to make the box move?
So we have to figure out what gets, we're going to have to deal with like the kinetic friction, right?
Well, first we're going to have to do a static friction analysis and see what the maximum static friction force is. So by doing that, we know that static friction is normal force times the mu sub s. So what's our normal force? Going to be the mass times gravity, because there's no other y components. So normal force is mg. .40 times 9.81, so 392. Once had a physics teacher tell me that on a test scenario, just say G is equal to 10. I'm like, no. But, I mean, honestly though, 392, 400, there's not much difference there. But either way, so we know the normal force is that, so our maximum force of friction is equal to, we'll call it max here also, is 392 times mu s equals 1/2 392 196.2. What shouldn't be a 0.2. One half of that would be a point. It's an even number, so there should be no decimal.
Well, I did times 5.81. So, wait. 40 from the phone, that'd be 392.4. Right here.
No. So just ignore the 0.4 then.
Okay.
When you're in the realm of 400.4 isn't going to make a big difference. So just 196. So that's our maximum friction force.
So anything over that will make it move?
Anything over that, it will move. But what we need to figure out is, will this box tip before P becomes larger than that? So what will cause P to tip, or what will cause this box to tip?
We exceed the kinetic friction before we exceed the static friction.
Well, it's not exceeding kinetic friction.
Or the value we get, we push and it tips before 196, right?
Yeah. And where will it tip about if this thing is going to tip?
That's a moment about like the bottom right hand.
This bottom corner here. So let's do a moment about that point and see where will our moment be not 0. So if we do moment about, we'll just call it A, since there's no other points labeled. Moment about A equals 0, hopefully. So we have our center of gravity is 0.5 away. That's going to be our 392 times 0.5.
Would that be a negative 396?
Yes, because it will cause a negative or counterclockwise tendency to rotate. So 392 times 0.5, and that's negative. Then we have P times 1.6, and that's positive. So 196 divided by 1.6.
Wait, actually, I think that the 392 is going to be positive because it's going to cause counterclockwise rotation, and then P is going to cause a clockwise. So I think that I was wrong. P is negative.
Well, as long as they're opposite signs, it will work out the same either way. Sorry?
P equals 122.5.
P equals 122.5. All right. So from our moment analysis, for this to not rotate, P must be less than or equal to 122.5. As soon as P gets a little bit above that, our moment is non-zero, it's going to tip. So if P is 122.5, our maximum static friction force is 196. Will this box ever move? No. What can we do to make it move?
Push lower.
Push lower. So let's try to now, keeping this, well, this force will be able to change later. Let's change the height to where? Give me a random value for the height that we think might work. Just 0.4? Or?
I think 0.4 should work.
Well, think about it in terms of meters. If a human is pushing this, where is the lowest point you would be comfortable trying to push?
Half of that.
You could try pushing it 1. I mean, if you want to line it up with G.
If you want to line it up at G. So let's try H equals 1. Just label that as H so it's known now. So now if we do our moment about A, we have the 392 times the 0.5. So we still have a 196, but now P is going to be P times 1. It's just P. Now P has to equal 196. So if P is less than or equal to 196, the box will tip, or will not tip. If it's greater than 196, it will. Our maximum static friction force is 196. So if we push with exactly 196, the box will not tip, but will it slide?
Or slide.
It will not slide.
It will stay stationary.
It will stay exactly stationary.
So do we even need to use the sub K?
Not with how this problem was done right away, no. But rest assured, it will be given to confuse you if it's not necessary. Now, if if we move P a little bit lower still, say now try H equals 0.6. Do the same moment analysis. 196, 0.6 P. So now 196 divided by 0.6. P can be less than or equal to whatever that number is.
Yeah, because that's 326.7.
I'm sorry?
326.7.
326.7. So, and now as long as P is less than that, it won't tip. So now that it can be greater than 196, it can start to slide if you exceed that, and then you would have to take into account kinetic friction.
So what was the question? Like what were we originally trying to find out? Like, will it move?
The original goal for this was, can this box slide?
Oh, okay.
Is, will it be possible for this box to slide with that original H?
So generally, though, if we're pushing above the center of gravity, the box is almost always going to tip.
Most of the time, yes.
Obviously.
Unless you can counteract that by pushing up at an angle. Because if you can push up at an angle, even if you're pushing up here, you're pushing up at an angle, that can decrease your normal force, which will decrease the force of friction. So you'll see a lot of times, and it's actually recommended, if you're trying to move a heavy box, you usually don't push, you pull instead. So tie a rope around it and pull it up that way. It decreases the normal force, which will decrease the friction force and allow it to slide much sooner than normal, so you can apply a stronger force without causing tipping.
So the point of acting an angle is to reduce the normal force, right?
Yes. The only reason you would ever, because you also have to realize, thinking about mechanics, if you're applying a force at an angle, if I can apply 200 newtons, then I would do the most work if I could push it straight. But if I push it at an angle, I'm losing some of that sideways force, because now it's just 200 times a cosine of whatever angle. But if that allows it to slide before it tips, I would rather do that. I'm still exerting the same force, but now I'm actually being productive rather than breaking the box. So if that question makes sense, we now have 20 minutes left for just general questions about anything. I know you wanted to look at a hydrostatic pressure problem.
Do you have like a list of all that you can do?
I didn't look through it and actually make a list of problems, but for Mackey's class, most of these problems were very similar to what he's done on quizzes and homeworks and stuff, and since that's where he draws his test problems from.
Are you talking about Zoran or are you talking about...
Dr. Mackey. Zoran, I don't know how Zoran makes his tests, so I can't really speak too much for that.
So has
So-
Matthew's tests been a lot like his quizzes, I guess, and his
Well,
homeworks?
every single test that Mackey's given, and he's even told you this beforehand, one problem comes from the homework, one problem comes from the quizzes, one comes from the lecture, and one comes from the textbook,
And then one from WebAssign.
and one from WebAssign,
That's-
mastering, whatever you want to call it. He takes one problem that he's assigned, changes the numbers around, but it's the same exact problems. If you've done all of your stuff for that class, you have done every problem on this test. So my best advice would be, if you have all those old documents, go back and redo any and all homeworks for this section that you can do. I mean, don't kill yourself. If you do, the finals tomorrow at what,
like,
4?
Yeah.
If you don't know it by tonight, you're probably not gonna know it for tomorrow. So work today. If you have no other plans, study, work problems, do everything you can do, but then don't worry about it tomorrow morning. Yeah, refresh, like look over notes, but don't spend time tomorrow trying to go through problems and memorize stuff, because it's just, you're gonna wear yourself out, and by the time you get to the test, you're just gonna hate life and not have any brain capacity left to actually take the test.
So, from what I've noticed, at least for like the machine problems, the best kind of way is to think from starting at look to see if we can find a 2-force member, and that's usually the best place to start, and then kind of work along until we run to a roadblock, and then go up to the next body and keep going.
Well, yes and no. Like we saw in the machine problem we did, we established that there was a 2-force member, but there wasn't anything we could do to start there. So you had to start with a different member first. It's good to identify that it's a 2-force, but with a machine, I would be willing to say you should always start with a member that has one of the applied forces on it. But if you start there, then you can use that information to get the others. If you're starting on the 2-force member, you're not applying force to that member, so you're not going to get anything out of it. So do you have a fluid
I've got a
problem? What page is it? I can,
Do you have the newest edition?
probably not.
Yeah, I've got the 13th edition. It's page 505.
I can not trip on things.
You can use my book if you need
All right. So we're going to take a look at 921. Where I put my pencil. I will draw this out real quick. We have about 15 minutes. While we draw, are there any other questions or concerns about anything we've done or haven't done yet? All right. This one's real simple to draw, so I think you should have it done by now. So what do we know about hydrostatic pressure and how it acts?
It increases as you go down, so it like linearly increases.
linearly increases the deeper you get, and if you are the body, how is the force applied to you?
Perpendicular.
Perpendicular to the surface. So we know at every point the force is going to be applied perpendicular to the surface. So for solving this problem, what does this problem ask us to find? Force on the gate?
It's undetermined magnitude of the hydrostatic pressure acting on gate AB.
Okay.
it's
So
the
resultant force. So we know that our overall hydrostatic pressure, I'm going to draw a second diagram. The pressure distribution will be roughly like that. So what we need to find out for the force on the gate is where the gate starts, where the gate ends, and then it's just a distributed load problem. So we know we're starting at 6 meters deep. What is the equation, or the
Isn't there, like,
strength of the hydrostatic force?
Yeah, and that would be resultant force, right?
Yeah.
Isn't the equation for finding this for like the water depth, it's like rho gy, right?
I believe so.
Yeah. But in this
Rho
case, it's
GH.
just gamma y. Because we already know.
Yeah. Rho g is gamma, and since it's water, we know gamma is 62.4.
Yeah.
So pressure is equal to rho gh, and it's good to learn that now, because as engineers you will take some class that involves fluids later, whether it's fluid mechanics for civils or I think it's just fluids for mechanicals, and you will use pressure a lot for a lot of different fluids, and you don't want to memorize 15 pages of tables of gamma. There are tables in the back of the book that's 15 pages long that's nothing but gamma and at certain temperatures in different fluids. Rather than memorize, they will give you a density, you know gravity, you know a depth. So it's good to learn it as rho gh, but now we understand that it's also just gamma times h. We'll call it gamma w because this is water. So gamma for water we know is 62.4. So, sorry? 62.4 is, yeah, pounds per feet cubed. So then we're starting at 6 feet, going down to a maximum of 10 feet. So our distribution is going to be 2.4 times 6, 62.4, 10. That's our system, but we're at an angle. So really, it's that same diagram, yes. Either way, your distributed load is a trapezoid.
So isn't that true with all, like, especially with all these underwater problems? If we're not like acting like straight from the surface, that would be a triangle.
Yes. Anytime you're working with a submerged body that's not flat, then your distributed load will be trapezoidal.
So if we were doing one with like a flat plate, would that be triangular, or would that still be trapezoidal, right?
If the plate is completely submerged, it will be trapezoidal. If it goes to the surface, you start at 0, and it would be a triangle. So with this distribution, what's the 2.4 times 6? 350 something?
374.4.
374.4. 624. I know. I think that alarm means we have 10 minutes left, so we should be able to get through this problem. So, do we want to solve this as a trapezoid, or do we solve it as a triangle and a rectangle? That's up to you guys. What's easier for y'all?
give you a
Probably
trapezoid.
trapezoid, right? Because there's an equation for it.
Yep. So 1/2 base 1 plus base 2 times the height. So base 1 is 374.4, base 2 is 624, add those together.
I said it all
Yeah.
that.
You know, is our height, is that 4?
Not quite. Is it? 949.4. 474.7 times h.
Which is 4, right?
No, that's what we're getting to right now.
So
Look-
is it going to be the hypotenuse of the triangle?
Yes, since the gate is on an angle, that's part of why you would have slanted gates rather than horizontal gates. Because now you're getting this same force as if it were applied directly straight up and down, but now it's acting over 5 meters instead of over 4 meters.
So yeah.
Yeah,
This is a
so you can use, it will take more material, but you can use weaker material, which means cheaper material. So the height would be 5 in this case, so that 474 times 5. 2373.5. And where does that act?
It's at like the bottom. It's like more towards the bottom portion, kind of like a triangle. It's like 2/3 from the small end.
If you do it as like a triangle and a rectangle, you would do the same thing as the M.
Yep.
Um,
You would do
times
it like a composite body, and say your centroid of the triangle is going to be right here. Centroid of the rectangle is going to be right here. Then you would do your x bar times the area,
Oh, so you would
Plus
do the
X bar
composite
times-
body problem.
yeah, to get the exact location. You would, unless you have a formula for centroid of a trapezoid, which there might be one in the book.
I think that he told us, like, Nick, didn't he say that if we asked for like the centroid of a triangle or a rectangle or something, he would give it to us? Or trapezoid?
Yeah, I thought I heard something like he said to treat it as a triangle.
I mean, you can do it easily this way, and separating the two, do it like a composite body, but if there is a formula for it, back cover,
Trapezoid area. C.
1/3 2a plus b over a plus b.
It looks like CX is like this more long. Yeah, this is what we're looking for, right? CX and CY.
Yeah.
So it's like H2A plus B3 plus A over B. And A over B is like the two sides, right?
Yes, that's the two bases. So, with this one being,
Is it probably just easier just to sum them up?
I would probably just sum it up, unless you want to memorize that formula. Then,
I'm sure like if we're on a test, if we wanted to ask for it, right?
yeah, I mean, it doesn't hurt to ask, and if you ask and it gives it to you, great. Otherwise, I would learn the process as just do it as a composite body.
And what did we say the result force was?
The total resultant was going to be 2373.5
Okay, and it's supposed to be 1/2 times 374.4 plus 624
times the height.
times 5. I got 2496.
So the 374.4 plus 624 divided by 2 times 5. 374.
Okay, yeah.
So, one more time?
2496.
2496.
So that's our resultant force, right?
Yes. That's your resultant force. And now you just got to figure out where to put it by doing the composite body problem. So, area of this triangle is 1/2 5 times 624 minus 374. And then 374 times 5 for the area of the rectangle.
So how do we know how to divide it into a triangle and a rectangle? Like how do we know the dimensions for it?
Because we already have the dimensions here and at this point, So if you just go from this peak here and go straight across, now you know that this rectangle is this dimension and the 5. And this, well, this is 624, you know this height here is this minus this. So if you guys can do the composite body part on your own comfortably like we did on the other problem, you'll be fine there. We are 4 minutes from out of time. So real quick, are there any other questions for me for anything, whether it's what the test might be like, which I don't really know, but any kind of generic statics questions at all?
Moment of inertia, I think you might test us on that. That's similar to like the centroid, right? It's like almost the same exact formula.
For moment of inertia, your formula, the formula for a centroid was x dA over dA. Moment of inertia was integral of x squared dA, and that's it. But for moment of inertia, it was y bar is x squared dA, x bar is y squared dA.
And then, will we have a, do you think possibly a three-dimensional moment of inertia or not really?
I doubt it. I mean, possibility, yes, but did you have one on any of the homeworks or quizzes, or on the mastering?
We didn't.
What was on mastering? I haven't done that yet. What was on there?
Well, it's there three-dimensional mastering.
There are?
I don't think so.
Oh.
We haven't done a lot of inertia, so I feel like if it's going to be a problem, it's going to be a simple one.
Show that for the people on the live stream, and if you guys feel like it, scan one of those codes on your way out. If you feel like telling them how you feel about study union, was the session good, was it bad, what could they do to improve study union as a whole. If you don't feel like it, don't do it. But
could you just like a brief explanation of what the parallel axis is? Because Matt, we kind of just like flew through it.
all right, parallel axis theorem is it's not too important for your test, so I wouldn't worry about it too much. But it's just a way, since he went over it so quickly, you didn't have any problems on it, so I doubt he would do that to you. But it's just a way to find the moment of inertia, or it's not really a centroid, but a moment of inertia really about an arbitrary point. So rather than, like, if you go to your moment of inertia table in the book, wherever it has that information, it'll show like a rectangle, and its moment of inertia about the base is the 1/12 b cubed h, but that's for about the base. What if you wanted to find the moment of inertia about the center? We'd use the parallel axis theorem, and it's that moment of inertia, the 1/12 b cubed h, plus some factor based on the distance. I don't know the formula off the top of my head, so I can't tell you exactly. But it's just like doing this is weighting a component divided by the whole. So it's the same way with the parallel axis theorem. You have the whole, and now you weight it with a component. But with that being said, it looks like I am out of time. So thank you for actually showing up and giving me someone to talk to other than myself. And good luck on your test.
You should have an hour here.
What?
You should have an hour this morning for that.